So, if we're going to start this mechanism, where should we start?
Alpha hydrogens.
Okay, so we've got a suggestion for starting for alpha hydrogens. I'm going to argue that's not a good place to start. It's not necessarily bad, but I would argue the reason you're starting with alpha hydrogens is you already know where you're starting to go. So if you don't know where you're starting to go, what should you be considering to look at?
Reagents.
Our reagents, okay? So we then have a reference for the carbonyl, okay? That's a possibility. When you're talking about the carbonyl, what are you actually referencing?
Carbon.
Okay, in particular the carbon, saying that you have a partial positive of that carbon. Why is it partially positive? The oxygen withdrawing electrons. I would also argue, not the place you should start. Identifying that electrophilic carbon is a good place. But again, probably not the best place to start. There are other things, or is it just those things? Just the ester is all we've got.
You have a strong base.
Okay, wait, we have what?
A base.
We have a base, but that's not what you said. What'd you say?
I said a strong base.
We have a strong base. Okay. What thing are you going to be most concerned about? Like the Hulk running at you or a wimpy kid?
Wimpy kid.
Because if he's running at you, he's got to have something up his sleeve, right? Okay. Strength is the biggest thing for us to be looking at. Okay? So when you look at a reaction, that's where you should be zeroing in, is where's the most negative, the most positive, because you need to neutralize that first. Okay? So when you say strong base, why do you say strong? Because to me, strong means negative, and I don't see that.
Well, you have a ionic compound.
I have a metal bonded to a nonmetal, which means I have an ionic bond. I could better split that bond apart by referencing this as a negative oxygen and the positive sodium. That negative oxygen is now my source of reactivity, and that's going to be my focus for the whole next sequence of reactions. My primary goal is to neutralize that negative. Okay, to neutralize that negative, what do I need to do? Find a positive. Conveniently, Rob already found a positive for us in the electrophilic carbon. So what could happen?
You can attack the carbon.
We should have it go ahead and attack the carbonyl. Don't get too draw happy with this yet. Right? Is that structure stable? What makes it unstable? The charge, negative oxygen. So how could I fix it? Okay, I could have that charge come back down, kick out a leaving group. Well, I already put on the OCH2, CH3, so
They're both the same thing.
that's done. Let's kick out the other thing. Some of you have already pointed out that that's the same thing. That if we go through and complete this structure, there's a CH2, there's a CH3, what did we end with? The exact same thing we started with. Okay? This is actually an important observation that's going to show up in 2 slides. Okay? The base that is used for the Claisen reaction must be the same as the ester part of our ester. Okay? Because if it is not the same, then this nucleophilic addition also happens. That complicates the amount of products we get at the end. Make sense? Okay, so yes, that could happen. That didn't take us anywhere useful. So while that was a positive carbon, I don't want to stabilize that positive carbon with my nucleophile. This is why I said don't draw anything, because what am I now going to do? Erase all the stuff that I've tried. Okay? So where else could I get electrons to stabilize that positive carbon? Alex?
The negative oxygen.
We already got it from the negative oxygen. We just tried that. Didn't work.
Oh, you get hydrogen.
You got a base and alpha hydrogens.
I have the alpha hydrogens, which is what Alex pointed out at the very beginning, which is why I went to you on that, by the way, for the record.
Sorry.
We could take the electrons in that bond and we could move them in to stabilize that. For that to happen, our base has to come in and remove the hydrogens. Okay? The result is what? What does that mean? What did you say that was? Officially the enolate, because it's negatively charged. Okay? The enolate has resonance, so we could look to that resonance to try and see something about its reactivity. Which of those two resonance structures is our reactive one? The red one with the nucleophilic carbon. I need to neutralize that negative carbon. Okay? Here's the next part that makes the Claisen difficult, just like the aldol difficult. How do I stabilize that negative carbon? I'm going to take unreacted starting material, so a second equivalent of my starting material, and line that up next to it. So my nucleophile can come in and attack, break that open, and we can get my reaction continuing. Here's the new red bond. Are you making noises because I missed something?
Nope. I just saw what you were talking about. Your reaction continuing.
Oh, okay.
It can spiral out of control, right?
What's that?
Because, well, once you get to the next, I'll ask.
Okay. Is that structure stable? No. So what happens?
You
Kick
can
out the
reform the
bond.
line one.
Okay.
Which is the base.
We can reform the pi bond, kick out a leaving group. Whoops. And we would reform the base. Yeah? Questions?
Can you hit that a third time? Because, or a second time? Because now you've got alpha hydrogens on the end.
Yes and no. Let's take a step back from that. This product is more acidic than our starting material. Why?
Diresonance.
I have two resonance through those carbonyls. So the alpha hydrogens now are more acidic. Okay? So that's something that we need to consider, and that's kind of where you're going, David, and we'll talk about that in a second.
Okay.
The other issue that we need to consider is that each of these steps so far are equilibrium reactions. Have we done anything to actually make our reactive species more stable? So let's take a look at the first step. The reactive species was a negative oxygen. When it reacted, what did it make? A negative oxygen. When it reacted, what did it make?
Negative oxygen.
When it reacted, what did it make?
Negative oxygen.
All of those steps did nothing to stabilize our charge. What does that mean about all of those steps? They are all reversible. Okay? So we should be including equilibrium arrows through the back of this. Okay? And this could be one of the reasons why Claisen gets to attach his name to it. Because if that's the case, this product shouldn't form. I shouldn't get any product, or at least not a sizable amount of it. Definitely not a 68% yield. Okay? Add to this that if we go through and look at the reactions themselves, our very first step is an acid-base step of deprotonating the ester. Is that hydrogen particularly acidic?
No.
No. Why? The ester does resonance to stabilize the carbonyl already, which means the alpha hydrogens are less acidic, which means that first step, unlikely to happen. primarily favors the reactants. Okay? The next step, this negative oxygen with a big old thing hanging off the end of it needs to get in and attack a sterically hindered big old thing, which means that step is not likely to happen. So we should fix that arrow too. Okay? We move to the next step. Okay? We kick out that negative oxygen as opposed to a negative carbon. So we might say that's a little bit more favored. Arguably, though, it's not a negative carbon we're kicking out, it's a negative oxygen. So that one is probably a decent equilibrium back and forth. We'll just accept that one as even. But in the 3 mechanistic steps we've run, 2 of them favor reactants, not products. Okay? Only one of them gets us some balance of products, which suggests that this reaction should not actually progress forward to any appreciable extent. Okay? Which does get to something that David might have been hinting at, and we already talked about, that those alpha hydrogens are actually more acidic in that product, which means what can happen? The base will pull them off, and we will progress to this structure with the negative charge. So I guess officially we should show in purple. Yeah?
What was that?
I think it kind of looks like Homer Simpson, right?
Hard to.
Okay.
I don't see it.
A little better? A little better? Okay. Or worse, depending on your perspective. And now every time you see a negative charge, you'll be like, God damn it, Mike. But at least you know what's going through my head every time I draw them. This is why sometimes you'll see me turn them sideways, because it's harder to see Homer sideways. It's got to be vertical. In any case, this reaction is an acid-base reaction that is actually irreversible. We're now forming a negative charge on 2 oxygens as opposed to 1. We have lots of resonance stabilization. This reaction works because that step is virtually irreversible. That's what's driving us to form our product. Okay?
So the equilibrium is just, you don't get very much of it, but as soon as it's like falling off a cliff, it's really hard to get up there, but as soon as you go down, there's no going back up.
Sure. I haven't fallen off many cliffs, but yeah.
I mean, like falling, like you climb and it's really hard to get to the top, but if you fall off, like that.
It takes a while to climb up to the top. Okay? And the driving force is to not climb up, right? We don't climb up cliffs very often, right? But once we get up to the top, if we fall off, we don't undo the death of that fall, right? We're done. Okay? That step isn't reversible. Kind of makes sense? So first Alex, then back.
So is that why it's refluxing for 4 hours?
So I would argue that reflux and that heat is to try and push to get that product, that the equilibrium heavily does not favor it, and we have to wait to get there to actually allow the dynamics to allow that to actually happen.
Okay.
That for the most part, it's going to favor the reactants. Okay? I would also argue this is probably why Claisen gets to attach his name to it, because we shouldn't expect it to happen. Oh, but it does. Why does it? That's that last purple step, and that's probably why Claisen gets to attach his name to it.
The purple hydrogens are the most acidic.
Yes.
There's no, I was wondering, is it just because it's so unfavorable to pull off, say, the other alpha hydrogen? And then
To do those blue ones?
down the road anyway. So just-
Yeah, if we look at those blue ones, those are alpha hydrogens that could be removed that could probably continue the cascade and continue to react. That might explain why the yield gets dropped a little bit.
But
Okay.
it's just such an
But
unfavorable
if we look at
on
the
end of the
actual acidity between those, that the purple ones are the higher strength, stronger acids. Let's do stronger acids. The purple ones are more acidic. That's what I wanted. More acidic than the blue ones. We're not going to get a significant concentration of the blue nucleophiles, which means we don't have to stress about that end of it. Okay? Is that structure what we want for our product?
No.
No, you'll notice that it's not actually there. We have that negative carbon. Okay? Deciding, should it attack another ester? remember, this had a steric issue already. What's going to happen to our steric issue now? It's even more sterically hindered, and it's less nucleophilic because we get the double resonance. Okay? That's probably going to hinder the reaction from running a third time or second time. Okay? But we still aren't at our product. That's why we have 2 steps. And the second step is to add H3O+, to put the hydrogen back on so I get the final product. Okay? Make sense? We good? Okay. So, I do like how Cardi breaks down his mechanisms. Mine are too messy to add all this extra information on. But we should be looking at naming each of the mechanistic steps, identifying that, because if you can identify what's happening at those steps, that can sometimes help you organize and structure where your reactions are going. So I do highly recommend you try to label out your mechanisms so that you can see those steps. Because Cardi's already done that, we won't do that, so we'll add the next thing that I think you should add to it. Okay, what's the next thing you should add? What did this species act as? That red box. It acted as an acid. What did it react with? Okay, that produced a product. Because that's an acid-base reaction, it's just a proton transfer. We've got proton transfer. We move to the next one. What did our carbon act as? This is a nucleophile. What did the blue one act as? An electrophile. Okay? The nucleophile is acting. So if we now look at where the chemistry is occurring, our chemistry is occurring right in there. Okay? The chemistry that happened is I broke a pi bond. So that would be an addition. What did I break the pi bond with? So I would call it nucleophilic addition. Kind of make sense? So if you can label what those things are doing in each of your steps, that can be an extra layer to kind of check a mechanism that you're creating. If you can't label the species in your mechanism, what does that mean? Your mechanism is probably bad. Okay? Sometimes you just got to do the best you can do. Drop something down as quickly as you can. If you got time, try and put in those labels. Or if you're going through it and you're like, damn, what the hell happened? Something's not adding up right. Okay? It's possible that if you just go through and label nucleophile, electrophile, or acid or base, that you'll see the mistake and you can fix it. Okay? Make sense? Okay. So, our complications. What can that strong base act as? Or sorry, that strong reagent act as? We've got a negative ethoxide in both cases. In one case, it can act as a base. In the other case, it can act as, okay? Because there's 2 options, we get 2 potential pathways that we'd need to be concerned about. Okay? If it acts as a base, what product am I going to get? Just that step. Okay, I would get the enolate. I'm going to get the negative carbon. It's going to remove the hydrogen. Okay, so the result would be with the negative carbon. We've got our resonance. We've got a nucleophile. We could do some potential chemistry with it. Okay, if it instead acts as a nucleophile, then what does it react with? The carbonyl. Okay, which one? In this case, it doesn't matter because they're the same. It could go through and attack. It's going to attack, break the pi bond, reform the pi bond, kick out the leaving group. Why does that become a problem?
Because the best leaving group in that situation is...
Not even that. I don't even care about that. Why does that become a problem? Look at the product. Give you some hints. It's not symmetrical. Symmetry in and of itself isn't a big deal, but when I look at that base in nucleophile chemistry, both of them are happening simultaneously in the reaction. If I'm trying to make that enolate negative carbon, okay, and I'm using ethoxide, yes, it'll absolutely deprotonate. It will also do a transesterification. That material can now do what?
Attack the enolate?
It can't attack the enolate.
The enolate.
Now base could attack this and turn this into an enolate, which means how many nucleophiles do I have? I'd have 2. But isn't there another ester on the other side? Couldn't my ethoxide also attack there?
Yes.
Yes, which means how many different nucleophiles would be floating around in solution? 3. Okay, at least. That's just the nucleophile side of it. You now throw an electrophile in also, and you get the potential for 3 products at a minimum, if not compounding. Okay? So when we're doing our Claisens, we need to make sure that the base being used matches the ester piece. Those pieces need to be identical. If they are different, it will mess with our Claisen reaction. Okay? Mess with the purity of our final products. Make sense? Okay. Could we do crossed reactions? So just like the aldol, we could have run this. Okay? What was the problem of that reaction? What's the most reactive thing?
The negative oxygen.
The negative oxygen. That negative oxygen is most likely to act as what?
The base.
Why not a nucleophile? I know that was the exact question you wanted me to ask, right? Why not a nucleophile?
There's no good leaving groups.
No good leaving groups is a possibility. What if it did act as a nucleophile? What would we get?
A negative oxygen.
Have it go through and run the reaction.
Oh, and the hemiacetal.
We'd get a hemiacetal, and our hemiacetals are unstable and revert back to the carbonyls. Okay? At least our non-cyclic ones. Okay, so yes, we have that chemistry available. It's a dead end. Okay? So that means it's going to act primarily as a base. So what is it going to react with?
Alpha hydrogens.
Alpha hydrogens. Where are their alpha hydrogens?
C2 and C2. Next to the aldehyde.
What is the problem with that? Which one does it react with?
Why not both?
So why not both is kind of a weird statement to make. Like, why not? Can't we just do both? Yes, it does both. Do we want it to do both? No. Okay? That makes a mess of products at the end. Okay? So how did we limit that? What did we try to do?
Can we change one of those reactions with a protecting group?
Okay? We could try and put in protecting groups. Protecting groups become problematic with an aldol or Claisen because we're generating a nucleophile due to alpha hydrogen enolate chemistry, and the electrophile is an electrophile because of
Electrophilic characteristics?
because of the carbonyl. So if you put in a protecting group, you get rid of the carbonyl, which means no alpha hydrogens and or no electrophile. So a protecting group is not a good idea.
You have 2 of the same molecules.
Okay, we could simplify it by just saying, okay, well, fine. I'll just get rid of one of them. Now there's only one possible nucleophile, one possible electrophile. That's fair. What else could you do?
Put them in at different times?
Put them in at different times. What do you mean? I like where you're going.
So, react the first one, make the, then you make a nucleophile. And then you put the second one in and act as a microphile.
Okay? Make your nucleophile first, then your electrophile. That's a nice idea. I like it. What's the problem with step 1 right now?
It's going to react with itself because you're creating enolane, and so
How much are you forming of the enolane? In that step 1, that is a reversible reaction is shown, which means some of it forms the nucleophile, some of it stays an electrophile. Just by mixing the ethoxide with that aldehyde, we're going to get some aldol. So how do I prevent that from becoming an aldol? So I like the idea of splitting. That's good. And change the base. Instead of using a base that gets us into an equilibrium, let's use a base that is not reversible, like we could use something like NaH, LDA. Use a non-reversible base. That way we don't have to worry about this imbalance. We form all of the nucleophile. We can now react that with our electrophile. That's going to clean up a lot of our side products. Okay? We will still get side product formations. Don't push that too far. Okay? But we clean up a lot of that. Okay? When we move to the Claisen, we're going to have similar issues pop up if we're going to try crossed reactions. Okay? So we have to be a little bit more careful. If I'm going to do a crossed reaction, I have to be aware of what base I'm using and when I'm using it. So if I was to try and use this reaction with that nucleophile, what's going to happen?
you're going to screw it up because it's wait a minute. Like if you did that,
If I did this particular reaction, what would I get for products? Just one Claisen product?
you'd get a mess.
I'm going to get a mess, okay? Because I have 2 potential alpha hydrogens. I have 2 potential electrophiles. I'm going to get a mess of products. So how could I simplify that to make sure that that doesn't happen? I could try and use a stronger base so we could split the reaction again, okay? I could go through and change one of my starting materials. With no alpha hydrogens, it can't react. Okay? Does that make sense? So we can modify those structures. Those are things that we have to consider when running the Claisen, particularly if you're going to see an exam question that says which of the following are your possible products, because you could encounter a situation where all of them are possible products. Make sense? Okay. So the other big thing that we have to deal with, okay, and actually I'm going to double back. When we look at this mechanism, this second to last step, removing that hydrogen, that was the one we showed in purple when I hand drew it, that is critical for this reaction to happen. Without that step, we do not get a Claisen result. Okay? Which means if we look at the overall reaction, how many hydrogens need to be removed from our starting ester? 2. Right? You have to have 2 alpha hydrogens on your ester. If you don't have that, you don't get the Claisen. Okay? So that's one of our complications. We have to ensure that we have those 2.
At least 2? Or 2?
At least 2. Okay? To ensure our reaction. Notice the reaction here, the product that we're getting is only 45%. Okay? Why might it be a 45% yield? What's the base going to react with? We got 2 structures, black or red. Why the red one?
Because the other one has no alpha hydrogen.
The black one has no alpha hydrogens. There's no acidic hydrogens that's going to react to the red one, which means that becomes the nucleophile. Which one's our electrophile?
The black one.
The black one can only be an electrophile. Could the red one also be an electrophile?
Yes.
Yeah. Did we use an irreversible base? No, so we could potentially have that attack itself. Okay? Which we might be seeing in the lower yield. Okay? So we can circumvent some of the problems by making sure our electrophiles are only electrophiles. Okay? Where it tends to show up, okay, is reagents like diethyl carbonate or the ethyl benzoate, both of which were examples that we already showed. Okay? We can also use ketones and aldehydes. Why can we use ketones and aldehydes? They have alpha hydrogens. So I can do not just an aldol, not just a Claisen, not just a crossed aldol, not just a crossed Claisen. I could do an aldaisen. Okay? I can take aldehydes and mix them with esters, and I can get all sorts of just crap flying out of this. Okay? Because that chemistry isn't all that extra fancy, we don't get to attach another name to it. Okay? But it's ultimately the same types of chemistry. Okay? Make sense? Okay. Aldols, we could do intramolecular aldol reactions. Okay? We can do the exact same thing with Claisens. We can do intramolecular Claisens. Okay? But for it to be an intramolecular Claisen, what do I need to start with?
2 carbonyls with alpha hydrogens.
So let's take a look at the reaction shown there. What do you think? Is that Claisen?
Yeah.
No. You don't have an ethers.
Okay.
Or an ester.
Dieckmann, I believe, is actually an intramolecular Claisen. We'll talk about that in a second. What is it?
That's a diketone, not a...
It's a diketone.
ester. It's not an ester. It doesn't have...
It needs to be an ester to be a Claisen. That's not a Claisen reaction that's being shown there. What reaction is being shown there? This is the aldol condensation. For it to be a Claisen, what do I need to do? What do I have to modify about that structure?
Make them O some things, like...
I need to have an ester.
Yeah.
Go O-methyl. Okay? Now I can call it a Claisen. What's the product? How is that going to change my product?
Your product's going to be an ester?
No, you're probably gonna
Draw it out. Okay, so let's take a look at this one. So I asked if you wanted alpha hydrogens, no, and I actually got a no from the crowd. Okay, so sometimes it's helpful to not let other people speak for you, just for the record. Okay, so we could go through and identify our alpha hydrogens. Our alpha hydrogens are located on a carbon that is next to a carbonyl. So we've got alpha hydrogens there. We have alpha hydrogens here. And we have alpha hydrogens here. Yeah? Okay. So all of those could be removed by our base. We weren't specific with the base, but I'm going to bet the base in this case was methoxide or NAOME. NAME? Sorry. Whatever. That would be our base. Okay, so when I went through and did this reaction with a couple people, I was intentionally a bit of a dick, okay, which is normal, right? So let's just, push that further and let's see where it takes us. Okay, we've been talking about Claisen reactions, which is looking at alpha hydrogens where? Near esters. Okay, so which of those hydrogens should I remove with the base? Blue one. Cool. That makes sense. So we could have my methoxide come in, remove that, take me across to my nice blue structure. Ding, 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 ding. Negative. A little bit sloppy. Okay, a lot of bit sloppy, but that's fine. Right? We could have the negative come down. And now we can have that pi bond, which is our nucleophile, attack what? The electrophile. What would our electrophile be?
The carbonyl on the other side.
The carbonyl on the other side. 1, 2, 3, 4. As soon as we do that, we should have a giant freaking red flag that we should probably stop drawing. But of course, because you have me as an instructor, 1, 2, 3, 4. At position 1, I'm connected to a carbon with the ester. Everybody see that? Okay. At position 4, I have the methyl and I have the O negative. So why should I have been like, dude, you should have just stopped? I form a 4-membered ring. You may not have seen that by doing the numbering. That's why drawing it out can be helpful. Right? Before you're like, oh, I can't form a 4-membered ring, so it must have actually been 1, 2, 3, 4, 5, right? Everybody see how I counted that? Okay. What you're now trying to do is force the chemistry to do what you want it to. Okay. This is why sometimes it actually makes sense to actually draw your active nucleophile. The active nucleophile puts the negative charge on this carbon. 1, 2, 3, 4. It does not put the negative charge there. Everybody see that? So this is why it can be useful to show the actual nucleophilic carbon, because that can allow you to see that a little bit cleaner. And maybe set it up where you don't go, oh, I'm just going to make it a 5-membered ring. You can't do that because that's not the nucleophilic carbon. Make sense? Okay. So, bad idea, 4-membered ring, shouldn't have done it. Should we have known that before we started?
Yes.
Why?
Because we've done it before.
No.
Because
4-membered ring, I should have not even touched the blue hydrogen. Shouldn't have even gotten to the point of asking 4-membered ring.
previously, we're not pulling off the, like,
yeah, I
we were
know.
reacting
'Cause
with
resonance.
the ester. So we created something that would then react with our original ester. And this, we're like attacking our ester first.
Not necessarily. What do you got?
Resonance.
What do you mean resonance?
Resonance with the ester, so that blue hydrogen's not as acidic as the other ones.
There it is. The ester, oxygen, is doing resonance into the carbonyl, which makes that blue hydrogen the least acidic of the bunch. We shouldn't be removing that hydrogen because it's not the most acidic. Does that make sense?
Yeah.
So that's where our failure actually started, all the way back to just acids and bases. Okay? So that was fun. We drew it all out, and now we get to erase it all. Kind of like every other class, right? I think people get sick of this. I sort of apologize. Okay? So we erased the blue one. So purple versus red.
Red.
Because purple gives you
Purple
some
gives
kick.
you
So I heard purple versus red, and I get red because purple is wrong. I don't really like that answer. We can do better than that.
Well, purple can be pulled off.
Purple can be pulled off. Which one is more acidic, purple or red?
Red. They're both equally acidic.
Their acidity is pretty damn close. Like, there isn't much of a difference there.
Wouldn't there be once you got the nucleophile on that? So if you end up with a primary versus
So-
a secondary carbon nucleophile?
There's an interesting argument trying to suggest something about the nucleophile. Primary versus secondary negative carbons. Except that is the least stable resonance structure, not the most stable resonance structure, so I should not be using that structure to evaluate. I need to be using the most stable. And if I go through and use the most stable, we're talking about the negative charge there versus there.
So which one's more stable, you said?
So the question that I'm asking is which one of those would we expect to happen?
The red one?
The purple one.
The purple one.
Yeah, you know, how you pull them off is so different. Why don't you just pull off a hydrogen and put the two dots?
So remember, this is a named reaction. It shouldn't happen. That's why someone got to stamp their name on it. The chemistry behind it is just Claisen. So for this to stand out as something that's worthy of being named, there should be some chemistry in here saying this shouldn't happen. Why is the purple one more likely to be removed than the red one? It's the more substituted pi bond, and I'm using a base that is reversible that favors the thermodynamic formation. Okay? Before we get too excited and say, well, now we should draw our product from the purple one, you're right. The red one is the one that needs to get removed to make a stable product. Dieckmann condensation. Okay? The least likely hydrogen to be removed is the one that is removed. That's why Dieckmann gets to attach a name to it, because, hell, it shouldn't have happened. Why did it happen? Oh, it happened for the next reason, which we'll evaluate. If we pulled off the blue one, we got a 4-membered ring. If we go through and look at our reactive resonance structure, we're having that nucleophilic carbon attack, our electrophilic carbonyl, forming a 4-membered ring. So the instinct that you guys pulled on purple is bad is good. I like that. But I want you to follow through all of those steps along the way. Does that make sense?
So I was talking about earlier with resonance is that, or like the worse nucleophile, is that when you get the purple one, wouldn't it be, because there's still, because it's a negative carbon, it's either nucleophile or a base.
Stop. You're referencing a negative carbon. You're looking at the wrong structure. That's the problem with that argument.
Won't the resonance give you a negative carbon? Which is the
But you're looking at the least stable resonance structure to define stability. That doesn't work.
Or like downstream the reaction. Once you
Okay, so we could also make the argument, well, that once it's left, it's most stable. That's like saying chlorine, the acyl chlorides react faster because chlorine's a better leaving group. That's not true. That's not why acyl chlorides react faster. They react faster because they're more electrophilic carbons. It doesn't have to do with the leaving group. It's a question of where you're referencing. If you're saying, well, downstream, to get downstream, you had to get to that intermediate stage first. So you can't tell me downstream works okay if you can't get to the intermediate stage. Does that make sense? So you have to be careful pushing too far down the path to deal with it. So, and that's where I'm going to cut you off. Okay? So with our red structure, we now want to go through and run our reaction. 1, 2, 3, 4, 5, 6. 6-membered ring is going to be awesome. We can attack, break our pi bond. We can draw out our 6-membered ring first. We can drop in our numbers. I'm going to put 1 here, 2, 3, 4, 5, 6. At position 2, I have that carbonyl. At position 6, I have the O methyl and I have the O minus. What can happen?
Kick out the O methyl.
Electrons come back down, kick out the O methyl. I would end up with the diketone. Officially, that's not where it stops. We still pull off that alpha hydrogen, then we work it up with the acid workup, and we put the hydrogen right back on. Right? Okay. Does that make sense? We good? And David, you can talk to me after class on pushing it, but you're definitely pushing it beyond where your explanation needs to be.
I was just wondering, right, because it's all equilibrium, so we're going to get a teeny amount of red, even though.
Yeah.
Is that
You definitely want to stop pushing the direction.
Okay.
It's just going to be the best bet. Okay. So in our Dieckmann condensation, officially we're using 2 esters, okay, which adds a whole nother layer on top of it. Remember we said our blue hydrogen, the one that was next to our theoretical ester, right, from that old drawing, wasn't very acidic. Dieckmann takes it a step further and we use a diester, which means there's no acidic hydrogen. So even further, there's no reason for this reaction to happen whatsoever, except, oh, it does. Name. Okay? Notice this one gets a slightly different product. Why? two esters. The one that we worked with was a ketone and an ester. So we ended with slightly different products in those cases. The general mechanism behind both is still the same. Sorry. No, that was right.
But if we had two esters for the first one, that wouldn't work. Isn't it too short?
For the first one, we wouldn't have been able to do it with two esters because, yeah, it's too short. We have to have those extra carbons.
Why do they use T-butoxide instead of,
What do you think? Because that's kind of interesting. T-butoxide instead of...
you risk using, like, you risk, oh, wait a minute, T-butoxide started,
T-butoxide is sterically hindered, which means its nucleophilic characteristics are probably very, very limited. So we're probably not stressed about it doing a nucleophilic attack on the carbonyl. Why use T-butoxide? Slightly stronger base than the ethoxide. Why is that important?
Because you're not very acidic. So
The esters that we're starting with are less acidic, so we need a stronger base. Okay. Make sense? Cool. Okay. Where the Claisens really come into play is our malonic ester and our acetoacetic ester syntheses. Okay. What these are referencing is the starting materials that we're looking at. Okay. Most of our esters that we look at, we say we start with an ester, oh, it does a Claisen. Okay. Are we starting with esters here? Yes. What is different about these esters in comparison to the esters that we've had before? So we had an ester like that. We had esters like this.
there's something on the beta.
There's something at the beta position for the nice drawn esters. What's that something at the beta position? A carbonyl. What does that make these two nice structures in black that our red structures are not?
Acids.
The structures in black are actually stronger acids. Okay, why is that important?
Because this requires deprotonation.
All of these things are going to require deprotonation. What's special about the structures in black, in particular in reference to the bases that we could use? We don't need as strong a base to get those reactions to run. Okay, so it is nice for that reason. Okay, we have that double resonance. That double resonance gets us to the enolate faster. We've got a solid nucleophile that we can run through and do our reactions with. Okay, we talked about reacting these with other esters and types of Claisens and things like that, but what we can do with these is a little bit different. Okay, let's start with that here. Sorry, as I confuse myself. Let's start with the acetoacetic ester. Step one, I'm going to add a base. What base do you think I'm going to add?
NaOH.
NaOH is questionable. I could get away with it.
T-butoxide then.
Why am I saying that one's the best choice?
Because that matches the ester bit on.
That matches our ester bit. What's going to be the product of that first step?
Negative carbon in between the carbonyls.
Okay, we get our negative carbon in between the carbonyls. Okay? Because of that diresonance, what does that do to the strength of the nucleophile? It weakens it, which means more than likely that will probably not do what? A nucleophilic attack on our starting ester, which means we don't have to worry about a Claisen, okay? Or it's going to be a smaller issue. But I do now have a nucleophile. What could I react with that nucleophile? Electrophiles. In particular, I can react it with alkyl halides. In that alkyl halide reaction, because I have a strong nucleophile, good leaving group, I'm running SN2. In that SN2, I can now make carbon-carbon bonds relatively easily. Okay?
Hate to nitpick you, but that's wrong.
See if I can find it first. Fudge. Now I think I got it.
Stereochemistry is going to matter on this one, right? Because you've got a stereo center on that.
Do we have a stereo center? Yes, we do. So we could get a mixture of stereochemistry coming out of this. That stereochemistry is not going to be based off of our alkyl halide. That's going to be based off of our negative charge. Where are the electrons? Are they above the plane or below the plane?
Above which hydrogen we took away.
Does it depend on which hydrogen?
No, it's SP2.
It's SP2 due to the resonance. Those electrons are actually tied up both above and below the plane of the molecule. You're going to get a mixture of both. Because we get a mixture of both,
Stereochemistry matters.
because we get a mixture of both,
Stereochemistry does not matter?
stereochemistry does not matter. We don't need to stress about it because we're going to get both equal amounts. Okay? So we're going to end up getting a racemic product out of that. Okay? Could we tweak it? Could we add things that have chirality to force one over the other? Yes, absolutely. Don't worry about it. Don't do that. Okay? Unless you really want to, in which case don't ask me about it. Okay? All we got to do is recognize that chemistry. So we've done a cool thing because we've now done carbon-carbon bonds. It ties all the way back to Unit 1 because we're using SN2 dynamics. And we say, cool, that's fun enough as it is. That's actually not the reason we do these reactions. The reason we do these reactions is actually the very next step. And the next step, I'm going to add H3O+. Okay? And I'm going to add a little bit of heat. No, why not? Okay? This is where things get interesting. When I add the H3O+ in heat, this is what happens. What happened?
You probated the oxygens on the other side.
This whole group did what? Somehow left the structure. Player 2 has left the game. Right? That's kind of neat. What makes that useful for us is it's not just that I'm adding carbons to my structure, but with this particular starting material, that acetoacetic ester dealey-bopper, I am specifically adding 3 carbons to my structure. Okay? That's neat because now I can make a structure 3 carbons longer in sets of 3s. That's kind of cool. If you don't think that's kind of interesting, if we think about how most biological molecules are built, they're built by sets of 5. Okay? Virtually all of our biological systems are built off of sets of 5 carbons. Sometimes they're built off of sets of 1, and really the sets of 1 is the loss of 1 carbon. What is the loss of 1 carbon from?
Carbon dioxide?
Carbon dioxide. It's the cleavage of carbon dioxide from a structure. That's how we removed carbons. Okay? Where are we getting the sets of 5? It's the unit called...
ENA.
No.
The other one you showed us earlier? The erase?
This would go all the way back to OChem 1 from my students. You undoubtedly forgot. Don't stress about it. It's an isoprene. So having a building block by which you can add more carbons is a really useful tool. And adding carbons in set numbers so that I know I can scale up by this amount is really useful. Okay? So the acetoacetic ester goes through and adds by 3s because I can cleave all of this off. So I'm adding these 3 carbons. What's the malonic ester adding?
Sets of 6.
I cleave the ester off. Whoops.
You're adding an ester.
I am adding an ester, but I care about the carbons. How many carbons am I adding?
3. No, 4.
2. The acetoacetic adds sets of 3. The malonic ester adds sets of 2 carbons.
If they're,
The whole rest of that structure is eliminated.
if they're already there,
What's that?
if they're already there,
What do you mean they're already there?
the carbon's already there, how you adding it?
So what we're doing is we're using this to make that a nucleophile. I now get a carbon nucleophile that can attack another structure. Okay? So what we're talking about is I have bloody bloop structure with a halide on it, and I want 2 more carbons. How do I get those 2 more carbons on it? I can use the malonic ester synthesis because that carbon can be made into a nucleophile that can attack and eject. Okay? I want 3 more carbons. I can use the acetoacetic, I actually had that right, the acetoacetic ester synthesis and have it attack instead. So what we're talking about is not these. These are the piece we're adding to our structure. Okay? What we're concerned about is what is that other piece. That other piece is typically what we're starting with. We're adding these things to it.
When you add the malonic ester, do you hits it?
Sorry, I didn't hear that part.
When you are doing the malonic ester synthesis and you add the acid where you eliminate the ether, does the other side go as well? So
Nope.
you get rid of that. So you
Nope.
keep that ether on there, but you just get
We're only getting rid of one ester. Okay? And that is important. Okay? That is tied to the chemistry of the remaining piece. Okay? It's tied to the chemistry of that remaining piece. Okay? And in particular, if we push this a little bit further, that part in red gets ejected not as an ester, it gets ejected as CO2. What is the charge on the carbon in CO2?
+4.
Positive, okay, or a partial positive. Oxidation state +4, you're right. Okay, which means what charge does that carbon have to be? Negative. I can't have a negative carbon though, right? What if it is resonance stabilized through an enolate? The decarboxylation works because of that resonance stabilization with the carbonyl. I can't get rid of this whole piece because if I get rid of that piece, I would now have just a negative carbon. Is a negative carbon stable on its own? No. The reason I can get rid of that CO2 is because of its proximity to the carbonyl. I have to have that carbonyl.
So do you just have to react again to get rid of that ester if you want? Just
So
carbons?
we'll push that to see what comes out. Okay? If we just wanted the 2 carbons and I didn't want the carbonyl or the ester, okay, when I go through that acid with it, what's the acid going to do to the ester? Here's an ester, I add H3O plus. What happens to it? I'll switch it up. I add H plus and H2O.
Make a carboxylic acid.
It does hydrolysis and it turns it into a carboxylic acid. If I don't want the oxygens there, how would I get rid of the oxygens?
Strong reducing agent.
I need a strong reducing agent to completely reduce away the acid. Okay, which would require steps. Do you know how to do that?
If it,
Yes, you do. Okay, you may not remember, that's okay. But we've talked about it. You could go through and reduce that away. Okay, LAH, let's just say that, because that's easier for me. The lithium aluminum hydride would reduce the carboxylic acid down to an alcohol, not completely get rid of it. How could I completely get rid of the alcohol? I could go the lithium aluminum hydride, for lack of better mental processing on reagents, the lithium aluminum hydride to the alcohol oxidized to the aldehyde. From the aldehyde, I could use Wolff-Kitchener.
SOCO2? I'm just guessing.
No. I could use Wolff-Kitchener. I could use the zinc and mercury and HCl. I could use the Clemenson. Okay, those reagents back in chapter 19 for reduction, reducing away carbonyl.
With the chloride.
I think I see where you're going. If we took that to the chloride, you could then do one of the lithium reagents to get it to the aldehyde, and then you could do those reagents that I was talking about, which I think would be faster than what I suggested. So, because I think this is our last big reaction, kind of want to talk about it. So here's the cool part we just walked through. Okay, relatively simple. Don't need to use strong bases. I get that negative nucleophile that can attack, get my substitution, put the R group on. Okay, the part that actually becomes cool on this is that next part. By adding acid and heat, I can decarboxylate. Okay, we call it decarboxylate because it is removal of carboxylate. Okay, how is it actually working? Okay, so this is neat. I always like kind of drawing out at least some of the mechanism. Okay, I'm not going to draw out the first part of the mechanism. The first part is going to take us to the carboxylic acid. Okay? We need CO2 to come out of this. Okay? Do we have the C? Yeah, we have lots of C's. Do we have a C that is most likely to be the C of CO2?
Yes.
Where?
The carbonyl is attached to the...
Carbonyl connected to those two oxygens, right?
Yeah.
Okay. For this to become CO2, the lone pair on this oxygen would need to do what? Go in, right? But it's got that hydrogen hanging out there. So here's what we're going to do. We're going to do a little tweak on the structure here. Here's our carbonyl. What did I do? Why? Visualization of what?
Hydrogen bonding.
There's a strong hydrogen bonding interaction there. That carbonyl can help remove that hydrogen. That would be an intramolecular acid-base reaction. What did we say about intramolecular acid-base reactions?
6 or more, you're good to go.
It's not what I was aiming for, but okay. 1, 2, 3, 4, 5. It's 5 or more. It's 5 and 6 is our transition state that works.
You missed one.
I did. 2, 3, 4, 5, 6. So it's even better. 6-membered ring is a transition state. That is a valid thing, and now it's a god-awful mess in there.
You think that out
Okay. So where do the electrons go that were holding the hydrogen there? To the carbon. But now the carbon would exceed its octet.
So it has to kick some out.
So we have to kick out electrons. What electrons do we kick out? The one headed towards the R group. Okay, let's just draw it that way for the moment. What do we have? We have the CO2. There's our CO2. It flies out of solution as a gas. We don't have to worry about it.
You also have a negative on the.
I would also have a negative charge on that carbon. Is a negative carbon stable?
No.
No, that's a horrible leaving group. You can't do that. Resonance stabilization with what? That carbonyl right next door
That's an enol.
would be an enol, and due to that keto-enol tautomerization, this reaction works. Keto-enols, super important. Is the enol stable?
No.
No, so what does it do?
Optimizes into.
It tautomerizes fairly quickly back out into our keto form.
You have to have something remotely acidic in order to do the keto-enol polymerization. Because like, can you prevent that?
You can do it under base, well, you can do it under base conditions, except it's not keto-enol. What is it? Enol means you have an alcohol. If you're under basic conditions, you wouldn't have a base, you wouldn't have an alcohol, you would have an enolate. You'd have a keto-enolate. So you can do the keto-enol tautomerization under basic conditions as well. Yes, you need something remotely basic and something remotely acidic in either circumstance. Okay? The dodge that I pull all the time, HB and B. Technically, I'm jamming this all into one step. This is bad because I have three things in one mechanistic step. Okay? But that's the beauty of this. The decarboxylation reaction works so long as you have what is known as an alpha-beta keto ester. The ester is the primary part of that name, so it ends the name. So there's our ester. Alpha, beta, at the beta position, what do I have? I have a keto. Okay, why do we call it keto and not ketone? It just needs to be a carbonyl. Okay, we are not specifying what continues out that side. That could be an ester. That could be an acid. It could be just a ketone. It could be an aldehyde. It can be anything. As long as you have that beta carbonyl, you're good. So you're looking for that alpha-beta positioning. You got that unlocked, the whole mechanism runs through your enolate intermediate leaving group. Okay? Which is kind of neat. Carty does a much better job of showing the mechanism. He even goes through and shows the rotation behind it. He pushes it a little bit further, okay, because that mechanistic cycle that he's showing there, okay, ends in a better structure than I showed. Why does it end in a better structure than I showed?
It's uncharged.
It's uncharged. The structure I showed had a positive and a negative in it. I was trying to highlight some of the reactivities behind it. Okay? We then tautomerize out to the ketone. So, again, where it's used, if we did something like the acetoacetic ester, we've got our larger structure as the halide. I do the acetoacetic ester synthesis, which really just means attach the larger halide structure to that carbon. Okay? Then do the decarboxylation, which ejects off the ester part, and I'm left with those extra 3 carbons in the carbonyl. It's a nice little way to connect 2 carbon chains relatively easily and with relatively minor or mild conditions with minimal side products. Okay? Malonic ester does the exact same thing, except instead of starting with the acetoacetic ester, we start with malonic ester. That's it. Okay, that's the only difference. Okay? The rest of the chapter talks about protecting groups for carboxylic acids and amines. Okay? The only reason why I'm talking through this is they're protecting groups. What did we say about protecting groups? We typically want to avoid them. Okay? You might see them pop up. Reviewing them, not a bad idea. I'm not going to explicitly test on testing groups. Okay, so you don't need to freak out about those. After that, we've got a big synthesis question, which we can talk about Monday. Okay? Just to give you an idea, I ballparked this out as 11 steps. Okay? You should be able to do this one. Okay? But I think it comes out at about 11 steps. So see what you can come up with. We will spend some time talking about it on Monday because I think it's a decent way to kind of review all of our reactions. Okay? After that, what does that say at the top? Optional material. Okay? What this is talking about is a whole bunch of protein chemistry stuff. Okay? Proteins are useful because they have carbonyls. Okay? Or proteins are useful because we're made of proteins. That's why they're useful. Okay? So if you were interested in biochemistry, you would see reactions that are discussed in this optional material. Okay? I will probably breeze through some of it on Monday, but I don't plan about talking a lot about it. Okay? I do kind of expect that you should read it. I'm not testing you explicitly about it. Okay? Which means Monday is largely review. Okay? I want to do the synthesis, but that's really all I have in mind. So if you want something to be discussed prior to the exam, Monday's a good time to bring that in. Okay? Homework questions, anything. Make sense? Okay.